We're going to talk a little bit more about fuels, and we're going to dive into a couple particular factors that help make aviation fuels what they are and distinguish them from automotive fuels, for instance. So, we're going to look at this a little bit. So, what you'll probably recognize over here is our chart of aviation specific fuels. Now, one thing you'll notice is you look at the maximum amount of TEL in milliliters per gallon. And you notice that the largest one we have right here is the old green format, which we really don't see very often anymore, if at all. And that was a pretty high concentration of TEL. That TEL is tetraethyl lead. And so that lead is something that we use to prevent detonation. That's important to point out because there's two factors here, critical pressure and critical temperature. Both of those will lead fuel to detonate, and that's not what we want. Detonation for the being able to understand what we're talking about here, detonation has the effect of going far beyond what the fuel is supposed to do when it burns. In fact, typically what happens is because of the conditions within the cylinder, the flame front moves so quickly, we're talking a difference of maybe like, oh, I think like 150 meters per second to way over like 9,000 meters per second or fit per second. I can't remember which one it is. It's been a little while on the chemistry side of it, but either way, the flame front moves so quickly that it compresses and superheats the remaining fuel air charge in such a fashion that it goes above its critical pressure and temperature and causes it to explode rather than burn. That has a very hard impact on the parts inside the engine. It's so hard, in fact, that you can actually hear it audibly outside of the engine. It's something we call pinging, which is very, very bad on the engine. It can cause a lot of damage to the cylinders and to the piston faces. So in order to prevent that, we use an additive, this tetraethyl lead. Now, the whole point of this is to improve the anti-detonation characteristics of the fuel. Now, there's a couple things about lead. Number one, we've learned that lead is not particularly good for the environment. It's not particularly good for people. And so we really don't like using that in fuel anymore. Additionally, we found out that lead is somewhat problematic in the fact that it is going to cause fouling of spark plugs and components within the cylinder if too much accumulates. And that's where these two chemical compounds come in right here, ethylene dibromide and tricresyl phosphate. Both of those are used to do what we call scavenging lead out of the cylinder. So that chemical that's an additive in the fuel, its whole purpose is to break down and dissolve the lead and allow it to be exhausted out through the exit of the cylinder. Now, one interesting thing about the lead is while fouling is a bad thing, oddly enough, lead can actually improve the lubrication qualities of the valves themselves. However, too much can actually cause the valves to stick and they can stay in an open position, which can cause anything from just bad compression tests all the way up to causing potentially valve train damage and or having an interference issue with a piston where we end up shattering a valve or something like that. So it can cause some pretty serious issues. That being said, you can see that what we use right now, 100 low lead, by the maximum TEL allowed in milliliters per gallon, is actually substantially lower than what we used to use in the green fuels, which is up to 4 milliliters per gallon and significantly different from what we had in the red fuels. This 80 octane or the 8087, the old rating for it, was actually used a lot with very, very small aircraft. We're talking, smaller than 200 cubic inches of displacement. So things like, Piper Cubs, Champs would use the red fuel and this 80 grade. And actually, what we talked about in the previous lecture about the differences between automotive fuels and aviation fuels, especially when it comes to things like Reid vapor pressure ratings and that kind of thing, is when the 80 grade of fuel was phased out early on, a lot of operators were trying to sneak automotive gas or MO gas into the airplanes just because it was hard to get, but it wasn't formulated for what the aircraft needed for a couple different ways. First of all, obviously the vapor pressure did not match, so it wasn't going to work at altitude. The other thing has to do with the way that they reach that octane rating. So, a couple things here. When we talk about octane, we have two elements. We have isooctane, which is what gives us our good characteristics. So isooctane has a very high anti-detonation characteristic as a chemical compound, whereas heptane does not. It's very prone to detonation. And so the reason that we have both of these included is not because these chemicals get put into the fuel that we use, but rather because they're used as reference points. So if we talk about octane, if we have a gasoline with its own set of additives, so for instance, if we have a bunch of TEL packed into a fuel, if it has the same anti-detonation characteristics as 100% isooctane in solution, then it would be 100 grade or 100 octane. So that's where we get this 100. Conversely, if it had the same anti-detonation characteristics as a blend of 80% isooctane and 20% heptane, that's where we get our 80 octane. So when you take a look at what you see on the pumps when you go fill your car, it's the same octane rating. So we're looking at how it performs with reference to this isooctane and heptane mixture. But we're going to use different chemicals to accomplish that. And that's another one of the issues that we have with automotive fuels versus aviation fuels. So a lot of automotive fuels may end up using something called aromatics. Now, aromatics may sound familiar. Well, either if you're cooking with aromatics, oh, that was only funny to me. Or if you remember anything from General, you'll remember that when we talk about cleaning specific things, we have something called aliphatic and aromatic naphthas. Now, these aromatics, we're talking about the aromatic side of the naphtha family. And the problem with aliphatic naphthas is that they break down rubber components. Now, there's obviously a lot of seals, there's a lot of gaskets and things like that in an aviation fuel system, and a lot of them are made out of materials that will not react well to aromatic naphthas, or a lot of the things that they use in gasoline to either increase the octane rating or to help scavenge carbon out of the engine. So as a result, if we put those into an aviation fuel system, guess what? It's going to kill the system. We're done. Can't do anything about it. It's a big problem. And so it may not show up immediately, but eventually what's going to happen is those seals start to swell, they dry out, and then they crack. So you're going to end up with leaks in weird places. What can even happen is you start to get those seals, they'll chunk away, they go downstream, then you start seeing black chunks of rubber show up in your fuel strainer, and you know that you have a pretty significant problem. So that's just a couple of the major differences that we have between those two types of fuels. And as we move forward, it's important to understand why fuel does what it does and how it's made up, because it's going to mean there's different decisions for us. And for instance, back in the 90s, the Experimental Aircraft Association put a lot of time and energy into trying to figure out how to make automotive gas something that could be legally used on certain aircraft. So, for instance, most Lycoming engines, as I recall, are technically speaking okay to be used with MoGas, but that's just a difference between a couple different things. So it's important to file these away, but that's all we have as far as fuel breakdowns and the components within. We'll end up moving on to how that fuel gets into the engine as we dive into fuel meters next.